Okay, so for part two about this unit, I've already run into some problems that would require some troubleshooting, so I thought to include that in this video. It started as an intermittent reset, meaning that the unit would start to do a countdown on the front display for no apparent reason, and then would go back to normal operation. In fact, the first time this happened was at the end of part one video, which I did not include. Mainly because it was the first time it was being powered on after decades of being stored in an attic, and it continued working flawlessly. So I didn't think much of it other than that it must have been a fluke. But then over the course of a few days, it started to happen again and again, and it would also occasionally fail to do a countdown upon power on, meaning that you would hear the power on, but nothing would happen on the front display, no lights or any activity. And that's what's happening now, which I'm about to show you. My hunch is that this is likely to be a supply voltage issue. So I've removed the top cover and connected these 3 meters here to do a test of supply voltages. This analog meter is set to 10 volt DC range, which is connected to measure the 5 volt DC. So that should be right in the center of the scale. And these two digital meters are connected to measure the plus and minus 15 volt DC. So let's go ahead and give it a try. And you can see that the voltages are not right and the front panel is completely dead. Okay, so let's have a quick look at the circuit diagram again. We looked at this at the end of the part one video. I've highlighted the three voltage regulator circuits, the plus and minus 15 and the 5 volts. And this protection circuit, I thought we'd zoom into this section to take a look at this reset capability, as well as the overvoltage protection, which is an important safety circuit. They're using an SCR in here, a silicon control rectifier. We could think of it as a diode with a control pin as a gate, which is ordinarily grounded through this pull-down resistor. So normally it does nothing, it's turned off, but we can see there are 3 ways to override and turn it on. The first one is this Zener diode. Is placed right on the supply line. So if this supply voltage goes above the Zener voltage of 34 or 34.8 volts, then this Zener diode will start to conduct in reverse and it will turn on the SCR. Now, when the SCR is turned on, we can see that it just sinks the entire supply line right into the ground like a short circuit, and it does so to prevent damage to other circuits beyond this point. Of course, this supply line here should never be above 30 volts, but we can imagine a situation like a power surge through the AC outlet, or if we remember from part one video, the primary side of the transformer has 2 windings, one for 120 and another one for 220. So if the user plugs it into 220 by mistake when it's set to 120, that can also cause a surge. It would be very bad for the transformer and the rectifier circuits. But at least other circuits beyond this point will be shielded because of this short circuit here. So they're essentially using this SCR as a surge protector. Now, the other 2 ways of turning on this SCR is through these 2 PNP transistors monitoring the 15 and 5 volts. This one is placed with both emitter and the base on the 15 volts. So ordinarily, this transistor will be off, and so will this 18 volt Zener diode, 18.2 volt Zener diode will be off. But if the voltage of the 15 volt regulator starts to creep up for some reason, let's say to 19 volts, then we know that the voltage at the base will be clipped at the Zener voltage of 18.2. Therefore, the emitter would be sitting at 19, which would make the base more negative, and therefore turning on this transistor, which would then fire the SCR. And by the way, once the SCR is turned on, it doesn't matter if the gate signal goes away. It will remain turned on because that's how SCRs work. As long as this holding current is sufficient, it will remain turned on. So in that case, someone has to switch off the unit. That would be the only way to reset it. And lastly, for the 5 volt regulator, we have this PNP transistor with its emitter connected to the 5. And the base, however, is connected to the supply line through a much larger current limiting resistor, but we still have a Zener diode here at 6.2 to clip and limit the voltage at the base. So again, like before, if there is an overvoltage on the 5-volt regulator, let's say it goes to 7, it becomes more positive than the base, it will be able to sink in current to the base, turn on, and fire the SCR. Now, if this SCR is tripped, there would be no activity on the front panel, but we could still hear the fan. It would still work because it is connected directly to the AC outlet. So that sounds similar to what's happening to me now, but I don't think the SCR is getting tripped in my case, because if it did, there should be no voltage on the 15 rail. But I'm still getting at least 10 volts, so that can't be it. Now, this reference voltage here is also fed into two open-ended comparators, one for resetting the microprocessor and the other one to feed into the 5-volt regulator. And here's why. Because of this high-value current limiting resistor on the Zener diode at 5.1K, compare that to 130 ohm, there isn't enough current going through here to allow this Zener diode to reach its full breakdown voltage. So by somewhat starving it from enough current, it sort of teeters around that breakdown voltage, which makes this point more sensitive to the supply voltage fluctuations. So if the voltage of the supply drops a little bit, this point would actually rise a little bit, because the Zener diode would be actually more turned off. And the reverse would be true, that if the voltage here rises a little bit, the voltage here will drop a little bit, because the Zener diode will be more turned on. And that's why they feed that into this comparator as one of the controls for the 5-volt regulator. And finally, for the processor reset, in case of an overvoltage, they're using the same point here to feed it into a non-inverting input of this op-amp. And on the inverting side, they're using a simple voltage divider that sits around 5 volts. So normally this side is going to be higher, which sends the output high. And we see from the label, there's a bar over that microprocessor reset, so it's an active low. But the situation could be reversed, that if the supply line voltage starts to creep up, then this side could get higher and it will send a low into the output, which would reset the processor. So I'm guessing it's possible that there could have been some overvoltage issues causing my intermittent resets, but I'm just not sure at this point. So at any rate, these test points here are what we just measured, plus and minus 15, and the 5-volt test points. Instead of 15 volts, we measured just above 10.5 volts, and instead of negative 15, it was nearly 0. And instead of 5 volts, I measured on the analog meter just over half a volt. So with that, I think what I would do is to go back to the basics, look at the rectifier circuits, and see if I can find any bad components there. So just to show you that the transformer is still working fine, I'm still getting 24 volts and some change on one side and the other. And these capacitors are still behaving as they did before. So I don't see any issues with those components. Now I like to measure the voltage behind these power transistors, Q100, Q101, and Q108. We have measured these test points where on the collectors. I like to measure the emitters on those. So I can see at the emitter I have the higher than the 25. That's because after rectifier voltages are usually higher. So that's on the emitter on the Q100, and on the collector next to it is that 10.5 that we were measuring at the test point. And again, on this emitter is negative 28, and on the collector is that negative 0.1. Likewise, on the Q108 transistor, on the emitter we have 29, and on the collector, instead of 5 volts, we have the 0.5. So looking at the schematic again, these 3 power transistors, which are installed on the side on the heatsink upside down, and the pins are pushed through the sockets. Looking at those, I wanted to see if I find anything unusual with them. And I notice on Q101 transistor, that the collector, which happens to be the output here, is actually shorted to the ground. This would be it would be this transistor here. I can show you that. Put the meter on ohms and test the leads. And going from the collector of this transistor, which would be the center pin, to the ground, we measure 0, which is strange. And to isolate this transistor, I simply inserted a little piece of plastic. I don't know if you can see that or not. Just push that in between the pin and the spring. So you can see that the pin from the spring is now disconnected. And testing that on the circuit where the collector would be, it's still shorted to the ground. So the issue is not the transistor. Pull that out. So looking at the schematic, that would have been the Q101. The collector is shorted to the ground somehow. And the only components I could see was this diode CR114 or this capacitor C107, just to make sure I cut one lead on each side and tested them to make sure that they're not shorted. And the only thing that I could think of is that let's try to disconnect this side, which would be this here. And now we can see that the collector is no longer shorted. So now what I need to do is to follow that into the board underneath and follow that rabbit hole to see where I end up. Okay, one more quick test with the ribbon cable disconnected and those two components soldered back on. I want to see if we could give it a power on to see if we will have the normal voltages on those test points. Okay, so since that test didn't go well either, I decided to take the main board out to take a look at the back to make sure nothing funny is going on. With the 9 screws removed and the ribbon cables unplugged, the power transistors stay where they are, bolted on the heatsink, and their leads will just slide off the socket. Really nice and easy. And inspection on the back, I didn't find anything unusual. But when I rechecked the components that were suspect before, I find out that this capacitor that I've cut one lead off is actually shorted now. So I can show you a quick measurement on that. Here are the leads shorted together. I'm measuring 0. And when I measure this capacitor here that is disconnected on one end, is shorted. It's definitely a bad part. And just to recap where this capacitor is within the circuit, it's this filter capacitor that is shorted to the ground. This other capacitor here is actually an electrolyte capacitor that I did test that as well by cutting one end, and that appeared to be fine. Now on the last test, I had to disconnect the J2. That J2 ribbon cable goes to the generator board. And that ribbon cable gets connected here, which there is another tantalum capacitor that I found out that is shorted to the ground. I tested it by cutting one end, and just like this one here that I tested is shorted to the ground. And that one is located physically here on the generator board. I'll show you that next. So we're at the bottom board, the generator board, and that's the capacitor that I've cut one end and appears to be shorted. Put up here my digital meter so we can have a quick measurement. And as we can see, it's shorted. Again, no discoloration, no sign of damage, smokes or sparks, but internally shorted. But I think the good news is that these capacitors are filter capacitors, and they're not really critical to the operation. So I'm hoping that we'll give this another test and see if the voltages come back up the way they're supposed to. Okay, I have resecured the mainboard back in its place. I've reconnected the transformer, and I've only connected the ribbon cable for the front display. I have resoldered the diode and the capacitor that I had cut on one end, and the bad capacitor cut on one end is essentially out of the circuit. With the meters back in their place to do the measurement on the power on, I'm hoping to see normal power on voltages. Let's give it a try. Yes. Great. So we see normal power on and calibration errors, which is normal because the other boards are still not connected, but that's good news. Okay, but for the question as to why would this shorted capacitor here or the other bad capacitor that we found on the lower board, on the generator board, both of them are on the -15. This one is C107, and this is C107 here, and it's on the -15 voltage regulator. So why would a short on this regulator here cause problems on the other two? I mean, after all, this transformer is a multi-winding on the secondary with the center tab as the ground. So this side is on the negative, and the other side is isolated on the positive side. So what's the relationship? The fine print that is hard to read here, and it's cut off a little bit, it mentions that they track each other, and here's how. Let's take a look at the 5 volt. This is a switching power supply. Basically, this is a 555 timer that produces a high frequency for switching this transistor, and these op amps down here are sensing the output voltage in order to produce a feedback for throttling that frequency up and down based on the output voltage. So it's basically a buck converter that is able to take this 24 volt DC right from here and step it down by switching it at high frequency onto this coil and its filter capacitor. There's a bit of schematic missing here. There's supposed to be a diode here. This is not my printer. This is the PDF that is just scanned very badly. This is supposed to say 500 microhenry. It's this black cube here, and it's smoothing capacitor there. Anyways, the relationship is that these two op amps that are supposed to sense the voltage on the load side, they need to compare it to a reference voltage. And when we look closely, they're using the 15, the positive 15 volt to establish a 5 volt reference. We see that the 15 is the source. They're using a resistor divider to establish a 5 volt reference voltage. And they did not use a variable resistor here. These resistors are pretty accurate to 1% tolerance. So as long as the 15 is correct, then this circuit is going to work just fine. And then when we look at the positive and negative 15, these circuits are linear voltage regulators. They're not as efficient. They do produce some heat on these series pass transistors, but they are smoother and cleaner outputs. Very similar design to each other. In fact, these two op amps are on the same IC chip, and we do see a variable resistor here for adjusting the 15, but then it tracks the negative 15. So that's why when the negative 15 had a short and went to 0, it really caused a big problem on throwing both of these regulators out of balance. Now they do mention that in the, like I said, in the notes here, it's really bad scan and in the 1987 version, but I found a 1983 version that I will include here that is much cleaner. In there, it explains that the 5 volt tracks the 15 and the 15 tracks the negative 15 volt regulator, and it lays out the proper order in which they should be adjusted in case calibration needed. Now, another important thing that it mentions is that all these voltage regulators are not only current limited, as you would expect, but also have current foldback, which I'm really grateful for. That's the feature, I believe, that explains how and why excessive current was prevented in my shorted capacitor situation. A quick review for contrast, both methods can output the full amount for the current needed for normal load. So no difference there. But in case of a short circuit, the current foldback would reduce the maximum output current to a much lower, much safer value for the power supply, and much more likely to prevent component damage, either in the power supply or wherever the short is. And those maximum values for current limits and foldback are also listed in a table in the fine print. So while the supply voltages are back to normal, I'm not really sure what to think about this bad capacitor, because it was actually the first component that I tested. I cut one end when I was looking for a short, and it was fine. Remember, I was able to isolate the short circuit by removing the generator board, and then I soldered this capacitor back on, and the self-test of the processor board failed, and then I find out that now this capacitor has gone bad. So why did that happen? I'm not sure. The one next to it is also of the same value, 15 microfarad, but it is on the positive 15 volt rail. Is it possible that being on the negative 15 rail has something to do with it? There are also other tantalum capacitors on this board. These three over here, they are not of the same value. They're 33 microfarad, but I believe this one here is 15. It's also possible that both of those capacitors were gonna go bad anyway. It's just that once one of them gets shorted, the other one cannot, because there will be no voltage across it until the short is removed, like I did. So that can make sense too. Anyways, I hope that this is just a lucky case of a couple of bad capacitors. So with that, since the supply voltages are back to normal, I think I will go ahead and plug in the rest of the boards back in to their place. But since we're missing a couple of filter capacitors on the negative 15 rail, it's possible that there may be some excessive ripples on the rail. I doubt it, but probably a good idea to check the quality on that negative 15 rail with my oscilloscope in the next test. All right, so I'm ready to fire it up for a full test with all the remaining boards connected through the ribbon cables. I got a probe connected to the negative 15 rail into channel 2 at 5 volt per division. We should see a deflection down of 3 divisions. So with that, wish me luck. Hopefully there are no errors. Oh, good. Excellent. Great. So back in business. Fantastic. So the deflection on channel 2 looks nice and clean. Let's go ahead and increase sensitivity to zoom in. We'll have to switch to AC coupling and at 1 volt, there's a little bit of ripple. It's half a volt per division. Let's go ahead and put on the voltmeter here. So about half a volt of peak to peak. So a little bit of ripple. I'm not sure if that's, we should probably take a look at the positive 15 as well to see what that looks like. So I went ahead and attached another probe to channel 1 for the positive 15 rail, and we can see that's so the negative is down here, this trace, and we can see the top one here is less ripples, but overall it's not much. I put a cursor up here so we could measure. I measured this top one is about 0.1 volts of ripple, which is really minuscule in comparison to 15 volts. And this one down here probably around 0.25. I wouldn't consider that excessive, but probably has something to do with those couple of filter capacitors missing. So I will certainly replace those, but for now I think it's acceptable to do some basic testing. And another thing I just noticed that the slight jitter that is appearing on the supply lines, that seems to be related to how fast the oscillator internal frequency is. So if I bring this back down to near zero, or we can see that the internal oscillator yanking on that, but the ripples are still there, and the frequency of that ripple is much higher. If I bring this down to almost, we're sitting at 4 hertz now, so it's pretty obvious that there's some noise that creeps back into the supply lines. But in any case, these ripples are like the 15 volt ripples is more than 99% there. This is probably 98% there, and I'm sure once I replace those bad filters, it would be as good as the 15 rail. If you up the frequency again and try to measure that, throw on some maybe try to measure this one here, 1.5 probably. That may be related to the crystal oscillator or not, I'm not sure. But let's go ahead and do some basic testing of the output. Okay, I'm setting channel 1 to DC coupling at 0.5 volt per division, and I don't have a 50 ohm option on this scope, so I'm using a 50 ohm PNC. Let's go ahead and do reset. So by default it always resets to 1 kilohertz at 100 millivolts. Let's go ahead and bring that up to 1 volt and then reduce the sweep. Looks pretty clean. Nice sine wave. Go ahead and switch to square wave, triangle. Looks nice and clean. Anyways, everything seems to be working fine. I will go ahead and do more testing. There are a couple of unusual functions on this unit that I'd like to test out. One is phase lock frequency multiplier and divider. That is unusual. I'd like to find out more about that, and also I'd like to test out the arbitrary functions. But aside from that, I'm gonna go ahead and order the capacitors so I can replace them, and hopefully those ripples will go even lower than they are. One thing I just found out about the ripples on the -15 rail, just found this electrolytic capacitor in my toolbox. Not quite the right value. It's a 10 microfarad instead of 15. But I thought it's close enough to just momentarily place it across that cut capacitor to see what the reduction would be on the ripples. I know there are two of them. There is one on the generator board, but just to show you this one here, without touching anything else, and you see that it's a very good response in reducing those ripples. So like I said, there are two of them. I'll get those on order, and once they come in, I'll replace. But overall, I'm very happy that the unit appears to be in working status again.